Dear friends, in the earlier module, we have discussed the constructional details of Smith chart and the theoretical part about transmission lines, that is different formulae, etc. that also we have discussed. Now, practice makes man perfect. So, unless we have a practice of solving numerical problems, we will not be able to penetrate through the subject to accept the challengeable problems with transmission lines and many other electrical systems. So, we will discuss how to use Smith chart for solving simple problems to begin with transmission lines using Smith chart. And here we will adopt the method of discussing the problem and its solution by adopting a step-by-step procedure. For understanding the various steps, we will adopt one more convention, that the R equal to 0 circle, which is also called as unity circle in the literature, has a diameter AOB, where O is the center of the circle and A and B as the two extremities. Those letters, namely AOB, will not be found in the actual Smith chart. Please note this change, note this convention, and then try to understand the simple applications or the numerical problems discussed in this module. After completing this module, you will be able to understand the use of Smith chart for determination of basic transmission line quantities, the use of Smith chart for estimation of radially scaled parameters, the determination of input impedance of transmission line, estimation of different types of losses with transmission lines. There are a number of calculations that are useful while transmission of signal through a transmission line. Calculating the energy actually arriving at the load and the energy produced by the generator are of prime importance. Ideally, the load impedance should match with the characteristic impedance of the transmission line, so that all of the transmitted energy is available at the load. Any mismatch between the two impedances will cause back reflection of the wave, thus hampering the quality and quantity of transmitting properties of the transmission line. This aspect can be accounted for with the help of many quantities such as reflection coefficient, VSWR, different types of losses, etc. All such quantities can be determined using Smith chart. We will discuss about them with special reference to Smith chart with necessary discussion about the concepts not discussed earlier whenever necessary. To begin with, let us see how to plot normalized load impedance and admittance on Smith chart with the help of a simple problem. The statement of the problem is as shown. The steps are as follows. Calculate normalized load impedance ZL. Second step, find the point P of intersection of R equal to 1 circle and X equal to 1 circle on Smith chart. Point P represents this normalized load impedance. Step number 3. With O as center, draw a circle with OP as its radius. Step number 4. Join points P and O and extend the line PO to meet the circle at point Q. The point Q represents the normalized load impedance. Note the values of R and X at Q. The geometrical construction and graphical solution of the problem under consideration are as shown. Let us discuss the second problem. The statement of the problem is as shown. Here, given normalized load impedance, we will study how to find gamma, the transmission coefficient T, VSWR using Smith chart. For solving the above problem, follow the stepwise procedure as shown. As a first step, plot the normalized load impedance, that is point P, on the Smith chart. Step number 2. With O as center, draw a circle with OP as its radius. Let the circle intersect the radius AO in W and OB in W dash. Step number 3. From W, draw a line perpendicular to the radius AO. Let it meet the horizontal scale lines of radially scaled parameters corresponding to VSWR and reflection coefficient scale defined in terms of E and I in points S1 and M1 respectively. Step number 4. Then the number at S1 represents the magnitude of VSWR. The number at W dash also gives the value of VSWR. The number at M1 represents the magnitude of reflection coefficient. Step number 6. Extend the line OP to meet the circular scale marked in degrees to measure the angle of reflection coefficient at point T1. The reading at point T1 represents the angle of reflection. Step number 7. Transmission coefficient. From point P, draw a line perpendicular to AOB. Step number 8. Note the reading at the point N where this perpendicular line intersects the horizontal scale meant to measure the transmission coefficient on the last, that is fourth horizontal scale marked with transmission coefficient E or I. Step number 9. Extend the line AP to meet the circular scale marked in degrees to measure the angle of transmission coefficient at point V1. The reading at point V1 represents the angle of transmission coefficient. Let us see a new problem. The statement of the problem is as shown. Here, knowing reflection coefficient at one location, we will find the reflection coefficient with same magnitude at another location. For solving the above problem, follow the stepwise procedure as shown. Step number 1. From the horizontal scale calibrated to read magnitude of the reflection coefficient, find the point M1 reading 0.5. From point M1, draw a line WM1 perpendicular to the diameter AO meeting AO in W. Step number 3. Draw a circle with OW as its radius and O as the center. Step number 4. Find a point P on the circle such that the line OP, when extended up to point T1, measures the angle of reflection as 40 degree. Step number 5. From point T1, move towards the generator along the circular scale of angle of reflection to obtain the point H reading 88 degree. Step number 6. Extend the lines OP and OH to read the numbers N1 and N2 showing radial distances on towards the generator scales. Step number 7. The numerical difference between N1 and N2 gives the desired value of distance D. From N1 and N2, we can determine the minimum distance D as follows. If N1 is greater than N2, then distance is N2 minus N1 times lambda. If N1 is less than N2, then distance is given by 0.5 minus N2 minus N1 into lambda. Smith chart can be used to determine input impedance Zin of a transmission line in a very simple manner. As an illustration, let us discuss the solution of a problem both analytically and by using Smith chart. The problem reads as shown. The analytical solution can be obtained using the formula derived in one of the earlier modules as shown. Here note that the length of 3.125 lambda is equivalent to 0.125 lambda and beta L is pi by 4. Therefore, tan of beta L has value unity. Accordingly, the input impedance by using the formula comes out to be 40 plus J60 ohm. One may self-experience the mathematical labor involved in these calculations. The solution by Smith chart can be obtained in a very simple manner by following a stepwise procedure. Step number 1. Calculate and plot the normalized load impedance ZL on Smith chart. Let point P represent ZL. Step number 2. Join points O and P and extend OP towards P to meet the radial distance scale marked with towards the generator at point T. Note the reading at point T. Step number 3. Now here the length 3.125 lambda is equivalent to 0.125 lambda as explained earlier. Hence, from the point T, move a distance of 0.125 lambda towards the generator in the clockwise sense and stop at point T dash. Note the reading at point T dash. Step number 4. Join points O and T dash. Draw a circle with O as its center and OP as its radius, and note the point Q of intersection of OT dash and the circle. The point Q represents the normalized input impedance Zin. Step number 6. Calculate the input impedance as shown by multiplying Zin by characteristic impedance Z0. The solution on Smith chart is as shown. Let us discuss a problem wherein given normalized load impedance, we can determine the normalized line impedance at a distance d from the load. The statement of the problem is as shown. The solution is as follows. Step number 1. Plot the normalized load impedance, that is point P on the Smith chart. Step number 2. With O as the center, draw a circle with OP as its radius. Step number 3. Extend the line OP to meet the circular scale marked in degrees to measure the radial distance at point say L1 on the circle number 4. Note the reading at point L1. Step number 4. Now 3.3 lambda is equivalent to 0.3 lambda. Hence, add 0.3 to the reading on wavelength scale at L1. Move along the circle in the direction towards the generator and a point L2 reading the number L1 plus 0.3. Step number 5. Join points L2 and O. Note the point of intersection Q of the line OL2 and the circle of radius OP. Step number 6. The point Q represents the location of the line impedance at a distance 3.3 lambda from the load. Note the values of R and X corresponding to the point Q on the Smith chart. The actual solution on the Smith chart will look as shown. So far, we have discussed about the problems related with line impedance and some other quantities using Smith chart. Now we can have the determination of minimum voltage and minimum current along the transmission line as one of the important applications of Smith chart. Vmax and Vmin, those are the symbols which were used in the earlier module for representing these quantities. Now on the Smith chart, along the right radius OB, we have the location of Vmax whenever there is VSWR rho, and at the location of 1 upon rho, that is reciprocal of VSWR, we are having V minimum. Vmax and V minimum locations are very important and they are used in many calculations for finding out the values of reflection coefficient, transmission coefficient and so many other quantities. So let us see something about this. There are some important things which you should know about location of Vmax and Vmin on the transmission line, and that can be done by using Smith chart in a very nice way. Keeping these points in mind, let us see how Smith chart can be used to solve a problem related with location of voltage minima and voltage maxima. The problem reads as shown. Let D1 and D2 denote the distances of the first Vmax and the first Vmin from the load respectively. The stepwise procedure is as shown. Step number 1. Calculate normalized load impedance ZL as 2 plus J. Step number 2. Plot the normalized load impedance ZL is equal to 2 plus J on the Smith chart. Let point P represent the location of normalized impedance ZL. Step number 3. Join points O and P. Extend the line OP towards P to meet the distance scale at point say P dash. Note the reading n plus 0.214 lambda at P dash. Step number 4. From point P dash, move along the distance scale towards the generator, that is in the clockwise sense, and first stop at point B, reading 0.25 lambda corresponding to Vmax. Step number 5. Note the distance traversed from P dash to B in the clockwise direction. In this problem, it will be simply the difference between 0.25 lambda and n is equal to 0.214 lambda, which is 0.036 lambda. This gives the location of the first Vmax on the line from the load. Thus, we have d1 is equal to 0.036 lambda, which is 0.036 into 10 centimeter, which is 0.36 centimeter. Step number 6. For finding the distance d2, move along the distance scale towards the generator, that is in the clockwise sense, and first stop at point A, reading 0.5 lambda corresponding to Vmax. Note the distance traversed from P dash to A in the clockwise direction. In this problem, it will be simply the difference between 0.5 lambda and n is equal to 0.214 lambda, which is 0.286 lambda. This gives the location of the first Vmin on the line from the load. Thus, we have d2 is equal to 0.286 lambda, which is 2.86 centimeter. Step number 8. For determining VSWR rho, draw a circle with center O and radius OP and note the reading at point W dash, where the circle intersects the right horizontal radius OB. This number is the value of VSWR. In the problem under consideration, we have VSWR rho equal to 2.6. Step number 9. Now, in the problem under consideration, what will be the values of D1 and D2 if the line is terminated in the load impedance of 100 minus J50 instead of 100 plus J50 ohm? Read and think over the steps 4 to 7 carefully, and you will find that n is equal to 0.286. The first Vmax is at a distance d1 equal to 4.64 centimeter, and the first V minimum will be at a distance d2 equal to 2.14 centimeter, while VSWR rho has the same value 2.6. Let us see one more problem related with determination of unknown load impedance from the measurement of shift in the location of the first minimum under short circuit and loaded conditions of the transmission line. The problem reads as shown. For solving the problem, we should note that the problem A on the horizontal radius OA of the Smith chart corresponds to the short circuited normalized load impedance of the transmission line. Hence, in this problem, the first Vmin under short circuit condition is located at A. When the line is loaded, the location of this Vmin shifts through a distance of 0.11 lambda towards the load. Hence, from A, move a radial distance of 0.11 lambda along the distance scale towards the load, that is in the anti-clockwise sense, to reach the point N. Join the point N and O. Draw a VSWR circle, that is the circle of radius rho equal to 3 with O as its center. Note the point P of intersection of this circle and the line ON. Point P represents the normalized load impedance. Note the values of R and X at the point P and obtain the normalized load impedance ZL is equal to R plus Jx. It will be seen that R is equal to 0.6 and X is equal to minus 0.65. With this, in the problem under consideration, we get the normalized load impedance ZL is equal to 0.6 minus 0.65 Z. Use the values of characteristic impedance 50 ohm to calculate the load impedance as follows. ZL is equal to Z0 into normalized impedance ZL, that is 30 minus J into 32.5 ohm. Note that in this problem, it is not necessary to know the wavelength. Smith chart can be used to measure different types of losses during transmission of power using the transmission line. Return loss and mismatch loss are the main types of such losses. Let us try to understand some basic facts about such losses before we deal with Smith chart. Return loss has prime importance in telecommunication. It is defined as a loss of power in the signal return or reflected by the discontinuity in the transmission line. This discontinuity can be a mismatch with the terminating load or with a device inserted in the line. In principle, return loss is the difference in dB between the incident power sent toward the load and the power reflected from the load, thus bearing in a positive sign. However, it is usually expressed as a ratio of reflected power and incident power in decibels. Reflected power is usually less than the sent or incident power, hence return loss has negative sign. Return loss is related with many quantities like reflection coefficient, VSWR, etc. For example, return loss is equal to minus 20 log of magnitude of reflection coefficient. The mismatch loss measurement describes the amount of power that will not be available at the load due to the reflected wave in units of decibels. It indicates the amount of power lost in the system due to the mismatch impedances. The mismatch loss can also be calculated from the reflection coefficient with the equation as shown. To have some idea of calculating the values of return loss and mismatch loss, let us see a simple illustration. Consider a lossless transmission line with characteristic impedance 50 ohm perfectly matched with the generator but terminated in the load impedance 100 plus J50 ohm. The normalized load impedance will be 2 plus J1 and the reflection coefficient gamma will be 0.45 with a phase angle 26.57 degree. Using the value of reflection coefficient, we can calculate the return loss as follows. The return loss will be 6.936 dB. Similarly, knowing the values of reflection coefficient, we can calculate the mismatch loss as shown. It comes out to be 0.9826 dB. We get the same result using Smith chart. For this, follow the steps in sequence as mentioned here. Step 1. Find point P corresponding to the normalized load impedance ZL equal to 2 plus J1 on the Smith chart. Step 2. Draw a circle of radius OP and O as its center. Let the circle intersect the radius OA at point W and OB at point W dash. Step number 3. From W, draw a line perpendicular to OA. Step number 4. Note the readings at the points where this perpendicular line intersects the horizontal scales to measure the desired radially scaled parameters as shown. The first quantity is VSWR. Its magnitude is 2.6 and it is equal to 8.4 dB. The value will be found on lower and upper sides of the first horizontal scale meant for VSWR measurement marked with SWR/dBs. The number at point W dash also represents VSWR. The second quantity is reflection coefficient. It is 0.45 in magnitude and this value will be found on the third horizontal scale marked with RFL coefficient ERI. Reflection coefficient is the third quantity and it is expressed in terms of power. The magnitude is 0.20 which is 0.45 square on the lower side of the second horizontal scale marked with RFL coefficient P. Step number 4. Return loss will be approximately 7. It is written on the upper side of the second horizontal scale marked with RT and loss in dBs. Step number 5, transmission coefficient. From point P, draw a line perpendicular to OB. Step number 6, note the readings approximately 1.4 at the point N, where this perpendicular line intersects the horizontal scale to measure the transmission coefficient on the last, that is fourth horizontal scale, marked with transmission coefficient E or I. Step number 7, mismatch loss or reflection loss. Note the readings approximately 1 dB at the point N2 on the upper side of the second scale, where this perpendicular line intersects the horizontal scales to measure the reflection loss marked with RFL loss in dB. From the discussion so far, you must have noted that it is essential to know how to use the horizontal scales to be used for determination of radially scaled parameters using Smith chart. Let us see some simple problems for better understanding of the use of these horizontal scales. The first problem reads as shown. Obviously, we have to make use of the horizontal scales to the left on the central line. Let us have a look at these scales. The scale for reflection coefficient. On this scale marked with RFL coefficient E or I, find the number 0.62. Let V0 be the corresponding point on this scale. Through the point R, draw a line perpendicular to the horizontal scales. Let V1, V2, V3, V4 be the points of intersection of the perpendicular line with scales marked with SWR, dBs, RTN loss in dB and RFL coefficient P respectively. Note the numbers at these points from the scales. Then the number at V1 gives the value of SWR, the number at V2 gives the value of SWR in decimal, the number at V3 gives the value of return loss in decibel, while the number at V4 gives the value of reflection coefficient measured in units of power, which is nothing but the square of the reflection coefficient measured in terms of voltage or current. Thus, accordingly, from the Smith chart, we obtain the desired values as shown. Increase in return loss corresponds to decrease in the SWR. Return loss is a measure of how well devices or lines are matched. A match is good if the return loss is high. A high return loss is desirable and results in a lower insertion loss. Return loss is used in modern practice in preference to SWR because it has better resolution for small values of reflected wave. We are discussing about the mismatch loss. Why and where mismatch loss occurs? What are the sources of mismatch loss? The answer is simple. Any constituent part of the transmission line having input and output can be the source contributing to overall mismatch loss. An impedance mismatch between the RF port and IF port of the mixer, mismatch between the input and output in amplifier, mismatch in the transmitting and receiving antenna directly are some of the examples which suffer a mismatch loss. Filters, attenuators, splitters and combiners are some more examples which are responsible for generating mismatch loss. Mismatch loss can be minimized by selecting quality components for use in a well-designed system. Smith chart is used mainly for design and analysis of RF applications. Radio frequency is any of the electromagnetic wave frequencies in the range from about 3 kHz to 300 GHz. These frequencies are used for communication on radar signal. You will observe that in most of the numerical problems documented in textbooks and literature, the characteristic impedance of lossless transmission line is generally taken as 50 ohm. It is simply because it is widely used in most of the test equipment and data sheets. Besides determination of transmission line parameters and related problems, Smith chart has many other miscellaneous applications scattering parameters abbreviated as S parameters, noise figure circles, constant gain contours and regions of unconditional stability are some of the special applications of Smith chart. Mostly, Smith chart is used for systems in which reflection coefficient is maximum 1. In other words, we think of only the region within the unit radius circle. What about the outer part outside the unit circle? It be noted that the region outside the unit radius has mathematical significance in the case of systems having magnitude of reflection coefficient greater than 1. The question is, can we have such systems having magnitude of reflection coefficient greater than unity? Systems involving negative resistance region devices are one of such examples. The region outside the unit radius becomes mathematically significant in design of negative region resistance oscillators and analysis of amplifier stability. Smith chart plays an important role in obtaining impedance matching networks. We will discuss this topic with adequate details in the next module. Dear friends, as a summary, we can remember that Smith chart can be used in a very efficient manner, in a very simplified manner, to provide the answers for various types of physical quantities associated with transmission line, such as reflection coefficient, transmission coefficient, VSWR, etc. Different types of losses such as return loss, mismatch loss, etc. can also be measured by using the horizontal scale of Smith chart. Smith chart can be used as a powerful tool for analyzing any problem graphically. However, the quantities can be estimated analytically as well. Thank you.